Welcome back. Let us recall again what we were discussing in the last class. So, we are discussing about LP spaces. So, let me again recall that. Okay, so, omega an open set. So, okay, you get used to this notations. So, soon we do not have to write all these things in detail. So, for 1 less than p less than or equal to infinity. So, we discuss this space LP omega. Okay. So, these are all Banach spaces. So, we can use the tools from functional analysis as and when required. Okay. So, in particular this L2, this is the only space p equal to 2 is a Hilbert space. For p not equal to 2, LP is not a Hilbert space. Okay. So, only this L2 omega is an Hilbert space. So, and inner product here, so let me just introduce some notation also. So, if f and g belongs to L2 omega, so we write this as, so this is integration fx gx bar. So, if you are dealing with only real valued functions, so there is no need to use bar. So, this is complex conjugate. Okay. So, either way. So, at this stage it does not make any difference. So, either we can deal with only real valued functions or complex valued functions, no problem. So, one remark, so the elements of, probably you know this thing, but let me just stress that elements of LP omega are equivalence classes of measurable functions which are identified measurable functions which are equal to each other almost everywhere. Almost everywhere in omega, of course. Okay. So, as such we should be careful when we write equality of two measurable functions, but for as far as integration is concerned, so there is no problem at all. Okay. And such an equivalence class may contain a continuous function. Okay. So, if such an equivalence class contains a continuous function, it may not at all, okay, but in case it contains a continuous function, then there is only one such continuous function. So in such a case, we say that so that's abuse of notation, you can say. So we say that function is continuous, and this follows from this simple fact you can easily verify. So if f and g are continuous functions, defined on omega, and f equal to g almost everywhere in omega, then f x equal to g x for all x in omega. Okay. So this is because of the continuity. So just so with these few notions, so you already might know, but these are some subtle things we have to deal with when studying these LP spaces, because the measurable functions are need not be defined everywhere, and equality is always in the sense of almost everywhere. Okay. But as far as integration is concerned, so there is no trouble at all, and it is always cumbersome to write, though we are dealing with equivalence classes, it is cumbersome to write, to just write as simple function. Okay. So with this convention, so let me just discuss another important topic. So compact subsets of so we will see more of this in study of Sobolev spaces in LP omega. So LP omega is an infinite dimensional space. So as such, the compact subsets are not characterized just by closeness and boundedness. Okay. So in Rn, infinite dimensional spaces more generally. So in finite dimensional spaces, so compactness is equivalent to closeness and boundedness. Okay. So this is your Bolzano-Weierstrass theorem. Okay. So but in infinite dimensional spaces, so compactness certainly implies closeness and boundedness, but converse may not be true. A simple example, so let me just say that. Okay. So in little L2, so this is the space of all sequences which are square summable. So consider this unit vectors E j. So this is just 0, 0, 1, 0. So this is at jth position. Okay. So, consider all this E j. So, each E j has norm in this L 2. So, this norm is in L 2. So, 1 for all j. Okay. So, bounded. So, clearly this gives you bounded, and so if you consider the distance between any two vectors in this set, this is root 2 for all j k, j not equal to k, and that shows both the things, that the set E j is closed and no subsequence converges. Because their distance is always root 2. Okay. So, hence this set is not compact. Hence, E j is not compact. So, in a general metric space, so the compactness criteria. So, let me just state that fact. So, as a theorem. Okay. A metric space so probably you would have studied this in your topology courses, is compact if and only if it is complete in the sense every Cauchy sequence converges, and so this is the additional criterion. So, totally bounded. Okay. So, a matrix space. Okay. So, what is this total boundedness? So, let me just define that. So, a subset A in X is said to be totally bounded if given any epsilon positive, there exists x1, x2, xn in A. So, this integer n obviously will depend on epsilon, okay, positive integer, such that each x in A belongs to ball of radius epsilon centered around epsilon for some j. For some j. Okay. So, this that means this finite number of balls cover the set A, then we call that totally boundedness. Okay. So, but this is statement is for a general metric space. So, how do we transform this notion of total boundedness in a specific situation? So, suppose for example, we are studying LP spaces. So, how do you translate this total boundedness in terms of the topology of LP omega? Okay. One such result we have already seen. This is namely this important theorem, Ascoli-Arjala theorem. So, it puts the condition of total boundedness in terms of this space. The space here is the space of continuous function, this space Cx of continuous functions on a compact metric space. Metric space X. So, equipped with sup norm. Okay. So, on this space, the Ascoli-Arjala theorem tells what are the necessary and sufficient conditions for a subset of Cx to be compact. Okay. Since closeness is always a requirement, so it is sufficient to say that a set is pre-compact, that means its closure is compact. Okay. As far as this space is concerned, okay, the total boundedness is stated in this equibounded and equicontinuous. Okay, just look at what you have studied regarding Ascoli-Arjala theorem. It says that a subset of Cx is pre-compact if and only if it is equibounded and equicontinuous. Okay. And these are in terms of the continuous functions. Okay. So, we do not have to worry about the number of balls and that covering. Okay. So, these are verifiable directly with the knowledge of this Cx. Okay. So, you want such a condition for our LP spaces. Okay. So, I will just state that it is a lengthy proof, and that proof. So, this importance of Ascoli-Arjala theorem comes that even to prove that a set is compact in LP uses Ascoli-Arjala theorem, and one such thing we will see in the study of Sobolev spaces, where we actually prove certain subsets are compact. Okay. The importance of again compact sets need not be stressed. Okay. They are, you know that. So, whenever we find a sequence in a compact set, we can easily say that it converges. Okay. So, for that reason we always look for compact subsets. Okay. So, with this thing I will just state okay, this. So, compact subsets of LP omega. So, as I remarked earlier, many results which are true for p less than infinity need not hold for p equal to infinity, and this is one such result. Okay, so this is true. So a subset, so this is theorem, A in LP omega, maybe not, let me write K. K in LP omega is pre-compact. Okay, so this is, that is K bar. Again this closure is taken with LP norm. Compact. If and only if the following statements hold. So this is again translating that total boundedness to this specific space LP omega. Okay, so this is norm of F P is less than or equal to C for all F in K. So this simply says that K is bounded. Okay, so this is anyhow a necessary requirement, but it is not sufficient. So what are the other conditions? So just let me write that. So limit h tends to 0 integral omega P. So sometimes we may not write this dx all the time, so just integration. So this equal to 0 uniformly for F in K. So I already seen that every F in LP satisfy this. So this is nothing but the continuity in the norm, but here the requirement is this limit should be 0 uniformly for F in K. So I will explain what that uniformity means. And the third condition is only if omega is unbounded. If omega is bounded, this is vacuous, so we do not need this. Omega is unbounded, then integral omega intersection with mod x bigger than r, okay, this mod fx power p tends to 0 as r tends to infinity, again uniformly for F in K. Okay, so let me just say what that is. This. Okay, so so given, so that second, for example, the second condition. So given epsilon positive, there exists delta which depends only on epsilon and the set in question, okay, not individual function in the set, such that so one more thing. So this is okay. So for LP spaces, LP functions, it does not matter at all. So whenever this x plus h goes outside omega, you just define it as 0. So, last time I said that. So, you extend f outside omega by 0. So, no problem at all as far as integration is concerned, but later on we see such a thing is not possible when we go for Sobolev space. So, this integral omega f of x plus h minus f x power p dx is less than epsilon whenever mod h is less than delta for all f in k. Okay, so, this is the meaning of that uniformly in f. So, similarly for this third statement. Okay. So, with that we come to an end of this discussion on LP spaces, and now we move on to another important topic, namely Fourier transform. So, this is again very important. If you are studying for the first time, so you have to really work hard to grasp many concepts. So, unfortunately, we cannot go into detail of everything, but let me just say some important things which are repeatedly used in this course and perhaps also in the next course. Okay. So, let me start with the definition. Okay. Now, all the functions are defined on Rn. Okay. So, if I will just define and then we will continue in the next class. So, let me not write this Rn all the time. Okay, just simply write L1. Its Fourier transform is defined by okay. So, this is the notation. So, f cap of j. So, this constant I will make a remark of that. Okay. So, n comes from the dimension, and this again integral is always over Rn. So, let me not write that, e to the minus I x dot j dx. Okay. So, j is in Rn and I is the imaginary square root of minus 1. Okay. So, as such, even if f is real valued, so in general f cap may be complex valued. So, we may as well consider the f to be complex valued functions. Okay. Of course, there are for real valued functions f cap is also real valued. There are some examples. Okay. So, a word about this, why this nasty looking constant. So, we can simply forget that, okay, but it shows up in the inversion formula. If we omit here, it shows up with the square of this factor will come up in the inversion formula. But if we retain here in the inversion formula also the same constant appears. So, there is some symmetry. Okay. So, we will maintain that. And in some books, so this factor is also taken in the exponential. So, instead of simply x dot j, some authors put 2 pi x dot j, but then when we take derivatives, those again factors of 2 pi appear. Okay. So, in any case we cannot avoid that factor this 2 pi. So, let us retain that. Okay. At least we will have a symmetry in the inverse Fourier transform, that we will discuss little later. So, let me quickly say that. So, this since we are taking f in L1, okay, so immediately see that okay, there is no problem at all. So, this is I will just simply just write constant f. Okay. So, f cap is a bounded function when f is in L1. Okay. More is true. Okay. So, let me just state that thing. So, so this is fact. So, instead of writing proposition, theorem, so some are small results, some are somewhat big results. Okay, just let me write that. So, f is continuous and f cap j tends to 0 as mod j tends to infinity. Okay. So, we say that this is vanishing at infinity. Okay. So, f cap vanishes, and this is often referred to as, this is called in fact, okay, Riemann-Lebesgue lemma. Okay. Let me sketch a proof of that vanishing at infinity, and that also the same technique we can use it for proving continuity. Okay. So, let me just concentrate on that Riemann-Lebesgue lemma. Okay. So, proof, sketch, okay, all these okay. So, f cap j, let me start with that. So, I may forget this factor, but just keep that in mind, it does not matter. So, f x, so integration is over R n, so do not forget that. Okay. So, here I want to put a factor here, so namely e to the minus I x plus pi j by j square. So, since we are interested in what happens as mod j to tends to infinity, so we can take j to be non-zero and large. Okay. So, look at here. Okay. So, we are adding, so e to the minus I x j is there, and the second one, so that gives me e to the minus psi pi. Minus psi pi, that gives me a negative factor. So, this is just okay. So, there is no change at all. Okay. Now, you change the variables. Okay. So, let me just write here. So, f of x minus pi j by mod j square. This is just translation. Okay. So, now so we have two expressions for f cap. Okay. Just add them. So, therefore, so we have 2 f cap j so 2 pi n minus 2 integration f of x minus f of x pi j by mod j square. And we have already seen the continuity of an L1 function in the norm. So, you just take this 2 f j, so that tends to 0. So, this is okay. Let me write that. This is just f of x minus okay, and that tends to 0. Okay. So, same expressions and same idea will also prove the continuity. Okay. So, we will continue with this discussion on Fourier transform in the next class. Thank you.